Okay, so I just want to welcome you all to our first ever virtual Science on Screen. Science on Screen typically does not look this way, but I think if there's one thing we have all learned this year is that nothing is happening in a typical way. So we showed the film Tesla at the cinema, and now we are going to have a discussion with Kit Thompson and Andrew Clark from Cloud County Community College on alternative energies. For those of you who don't know, Science on Screen is a program that is funded through the Sloan Foundation and Coolidge Corner Theatre. We get a grant at Salina Art Center for this, and what we are trying to do is use movies as a fun way to introduce STEM topics and STEM careers to our audience. So this is actually the fourth year that we have done Science on Screen, and we hope to do it again. Typically we do it in April, but April was when we initially had the shutdowns, so we weren't sure how this was going to work this year, but this is how it is working. You could have come and seen the film Tesla in our cinema, and if you did, we appreciate that. But if you didn't, you can still participate in these discussions, which is something else that makes Science on Screen kind of fun. Next Monday night, we are showing the film Kajillionaire at the cinema, and then we will have a discussion at 7 p.m. online with Dr. George Yurkovich and Dr. Paula Freed, and they will take a humorous look, if possible, on what is a sociopath, and were the people in the film sociopaths. So we will talk about that. And then our final Science on Screen will happen on October the 26th. We are encouraging everyone to watch their favorite spider-based film and then join us at 7 o'clock on Zoom for a discussion with Dr. Justin Jones, who is the director of the Spider Silk Lab at the University of Utah, Utah State University. And he will be talking about the futuristic uses of spider silk. And the conversations that I've had with him are just fascinating. So I think it'll be a fun and interesting conversation, including learning how they produce spider silk from a completely different animal, because spiders are too small to produce enough silk to do some of these things that they're doing. So I think it'll be a really great way to wrap up Science on Screen. We, of course, want to thank Sloan Foundation and the Coolidge Corner Theatre, but also our local sponsor is Kansas Bankers Technologies. We appreciate them helping us out with this project as well. So I am now going to turn things over to Kit and Andrew, who are going to talk to us about alternative energies. One of my favorite scenes from the movie Tesla was when Edison was at a bar using his cell phone. And it was a very brief little scene that I don't know, like my husband didn't pick up on it when I was talking about it later, but I just found it fascinating that I think through a lot of the film, we were seeing Tesla's vision for the future, even though he didn't maybe know how to articulate it, but he saw these things as possible and these things that could happen. So this concept of Edison at the bar flipping through his cell phone, I just thought was a really humorous scene. But I think this idea around energy and how we create energy and what energy can be used for in the future is something that Cloud County Community College really embraced right as I was leaving the college, which I thought was an interesting thing. I think that's about the first time we got our first wind tower up there at Cloud County. So these guys have taken that program and really run with it. And I'm excited to hear about alternative energy sources. So I'm going to go ahead and turn things over to Kit. If you have questions, you are welcome to use the chat function, and I will feed those questions to the guys as I can. But now I'm going to turn things over to Kit Thompson.
Thank you, Misty. I'm Kit Thompson. I'm the department chair of renewable energy at Cloud County Community College. We have programs for wind turbine technician, photovoltaic installer, so solar energy, blade repair because the wind turbine blades need to get fixed. Substation technician, they handle the high voltage transmission, and then also drones. We joined in with a drone program because they're being used more and more for inspecting wind turbines, inspecting solar farms, inspecting power lines, but then also in so many other industries as well. With me here is Andrew Clark. I'll let him introduce himself.
Yeah, my name's Andrew Clark. I'm the one of the renewable energy instructors. We have quite a few that we all kind of specialize in something. I started off as specializing in the field training, as I had 5 years of experience in wind energy. And just 2 years ago, we started the solar energy program because we're trying to stay on the cutting edge. And we kind of seen the future is going to be solar and wind combined. And so we're kind of just a little ahead of the curve still, as we have very few actual solar farms, but rooftop solar is fairly integrated into society now. So we feel like we're right on schedule, maybe not too far ahead.
We felt that tying in with the Tesla movie, we would talk about AC and DC. You saw how Tesla, if you watched the movie, you saw how Tesla and Edison were battling about the pros and cons of AC and DC, alternating current and direct current. And that is one of the more obvious differences between how wind energy is harnessed and how energy is harnessed from the sun. Is one produces alternating current, that's the wind turbines, and the other, solar panels, they produce direct current, DC. So I'm going to start off talking about wind. I've got a little presentation. Just going to go over the basic science behind it, just really basic level stuff. To describe wind turbines. I'll try to highlight some of the misconceptions about how they work, and then I'm going to hand it over to Andrew, and he'll talk about the solar panels. So let me bring up my slides here. Okay. Is everybody able to see our wind turbines there?
Yes.
A couple of little ones we have up here in Concordia, and our students do practice climbing on those wind turbines. We really try to make sure we have a hands-on program here to make sure our students get that real-world experience for wind, solar, drones, and so on. Let's see here. If I can, there we go. We decided we'll go ahead and title our presentation Alternating Wind and Direct Sunlight, playing on alternating current and direct current. As I mentioned, how the wind turbines produce AC and the solar panels produce direct current. Let's see here. And you saw the clip of our 2 wind turbines. We also have a small solar farm as well. We've got 12 rows solar arrays producing, both of them producing electricity for our college here. So wind turbines, they're not actually a new technology for all of us. The earliest large wind turbine was built here in the US. It was in Ohio by Charles Brush. He built it in 1888 for his mansion, the charged batteries that he had at his mansion. And going back to the movie, so in 1888, Tesla was 32 years old. So it wasn't just Tesla, it wasn't just Edison. There were other folks investigating how to generate electricity, how to utilize it. But this is a good example of a really early wind turbine, a turbine being a rotating machine that generates electricity. Then they got bigger, so much bigger. Recently, of course, they've gotten a lot bigger, generating a lot more electrical power, and doing so with so much more efficiency. For quite a long while, wind turbines really didn't join the energy market for many decades. They just didn't have that much efficiency compared to other electrical generation systems. But over the past 30 years, there's been a lot of research, a lot of investment in how to more efficiently harness the energy in the wind. So what they actually do is they transform energy. they're transforming the physical energy from the force of the wind. If you're standing on a hill on a windy day, you feel like you're going to get blown over. It's a physical force with that wind. We are harnessing that and transforming it into electrical energy. We don't actually have any devices that create energy. One of the laws of physics is that you don't create energy, you don't destroy energy, you just transform it. And that's really what all of our power generation technologies are doing, is transforming one energy form into another. And that's what wind turbines do. They transform the physical energy of the wind into electrical energy. So let's start with the first step in that. Obviously, the wind is blowing on the wind turbine blades. And I think a lot of people think, well, the wind is pushing the blades. Not really. It's not actually quite so straightforward as wind pushing on blades, as though if you were holding onto a little toy pinwheel and you were blowing on it, you are pushing it into a rotation with the force of your breath. Well, that's not what works with a wind turbine. In fact, it's more like an airplane. It's relying on lift forces. So this picture here, that's like sort of a cutout view of a blade. That airfoil shape looks like a wing of an airplane. What happens is what we call Bernoulli's principle. It's a matter of air pressure. As the airflow goes over the top of the blade, it has to travel faster than the airflow that goes under the blade. And when you have a faster fluid, and a fluid is not just liquid. In the scientific sense, a fluid can be a gas. Even solids can act like a fluid. Air, when it's moving, it's a fluid. So there's faster air traveling over the top of the blade, slower air traveling underneath the blade. Bernoulli's principle is that you will have a high pressure with the lower velocity fluid. You'll have a lower pressure for the higher velocity fluid. And that's really what's turning the blade. The fact that you have a higher pressure on one side and a lower pressure on the other side. In the aeronautical business, we call that lift. There's a lift force that is causing those blades to keep turning. And really, it's like they are flying like an airplane, except they're fixed to a shaft. So they keep rotating around a fixed point. So you're not really watching the wind pushing the blades. You're watching the blades fly through the airflow from a fixed position. And so they keep rotating. The more, the faster your wind, more lift forces you're going to have. And so your blades on your wind turbine will move faster. So that's a really important concept, that it's lift forces. It's a matter of difference of pressure. This is a pretty basic picture here. So look more at the angles that are really happening. So let's say the bottom of this picture here is the front of the wind turbine, where you'd see the nose cone, and the back is more towards the back. That's downwind in this picture. Over on the right, and let me see if I can actually use a little marker here. I've mixed results when I try to do this in the class. So here's our wind. Our wind is blowing this direction. But it's not just the air that's moving, it's also the blades. The blades are turning. And so with the blades turning in this direction, the result is that the airflow is going to be in this direction. So with that angle of airflow traveling over our airfoil over our blades, here's where we're going to have the low pressure on the back side. The low pressure is on the downwind side. Here is where we're going to have the high pressure. This is the lower velocity air flow. The high pressure side is on the front. It's a little hard to see when you're looking up at those big wind turbines, trying to figure out how are they curved. You have the, basically you have the convex side on the front. I'm sorry, the concave side, sorry, concave side on the front. Let's say this is the nose cone shape here. You have the convex side on the back. That's very exaggerated, but that's basically the shape of these blades when you're looking up at the wind turbine. So the ultimate result of that, you have a perpendicular force here in red called our lift force. That's Bernoulli's principle. You have the higher velocity airflow on the low pressure side, and you have the lower velocity wind with the high pressure side. You end up with lift force. Drag is just the airflow working against the blade. Anything trying to push into airflow, there's going to be some drag. There's going to be resistance. And with this lift force, we want to maximize the amount of lift force. We want as much lift force as possible from our wind turbine blades. We want that to be the strongest force acting on these blades. Now, because they're at a fixed point, it's going to keep rotating in a circular fashion. We end up with the blade turning in this direction because of the dominating, the stronger lift force. And that'll be our torque. That'll be the rotating force acting on the shaft of our blade, because the blades will be attached to the shaft. Torque is what we really want. What we want to come from our spinning wind turbine blades. And at any point, please feel free to ask a question and stop me here. So we now have transformed the kinetic energy of the wind blowing into the torque, the turning force with the shaft. Let me make sure I got my chat window up here.
The question?
Yes, go ahead, Kristen.
Do you, is that just trial and error, or mathematically are you determining the length and slope and all that you need? At this point, you probably just do the formula. Is that right?
Let the computer do the work.
Let the computer do the work. Okay.
Back with Charles Brush, 1888, there was certainly some knowledge about forces, torque, certainly, but they didn't even have flying aircraft at that point. So still a lot of aerodynamic forces that they didn't understand. Now we have that knowledge, but it is very complex. Yeah. So I certainly would always just let the computer do that work. Let the computer simulations figure out some of the major factors that an engineer would put into the computer. What is the expected prevailing wind velocity for the design you're coming up with? What is the optimal RPM, rotational speed of your rotor? What's going to be the length of your blade? And then they start trying to figure out what's the airfoil shape? What are the curves that are going to be involved in their blades? Because it's a rotating set of blades, it's got a slower velocity on the inside. It's got a higher velocity out at the tips. They actually have to twist the blades. So if I were to try to draw that here, on the inside, the root section, it's very thick.
Yeah.
At the tip, it's going to be moving a lot faster. So they're going to twist it a great deal. Again, I'm very much exaggerating here in that twist.
Well, you can see that when you see them on a semi,
Yes.
going down the road.
Yeah, exactly. And that's one of the best ways to see it. You're driving behind one of those blades. You can see that twist. It's a computer that comes up with that. The computer decides how much of a twist is best for your targeted wind speed and rotational speed and so on.
So the old cute windmills that you see, I think they bring up water, don't they? But they don't seem to have that. They have a pitch on the blades, but they don't seem to have that different form. So something else is making that move. That's a different process.
It's still, depending on the design, most of them are still using lift, actually. It's just a matter of they're so much smaller. And depending on how far back you go, there might not have been as much aerodynamic engineering involved. I think if we look at the smaller ones that are new designs, they do have a twist in them. It's a slight twist because they're small. But the older ones that are either pumping water or, yes, some of them did also generate electricity, small amounts of electricity for remote farms. Yeah, it's still using lift forces for the most part, just not as efficient. A lot of research went into coming up with the current design, the huge industrial size wind turbines with the 3 blades that we see on them. Thank you. Good questions. I'm going to jump to my next slide here. I know that whenever I start drawing, I have to do a little more juggling to get my slides to respond here. Let's see here. Oh, let me close that. Okay. And then I have to go back and I need to erase all of my work there, so it's not so sloppy. Oh, come on, Zoom. Just give me the window I want. Honestly, I'm gonna jump back into it. Doesn't let me have a smooth transition for some reason. So I said we then have torque, that turning force on our shaft. And I'll jump back into this one here. Okay, so our shaft is the bolt or the nut that we're looking at there. The force, wherever our hand is on that wrench there, turning force. With our wind turbines, of course, it's a large steel shaft that we're turning, and it's the rotor, the blades, the wind energy, that's the force, the lift force acting on our blades. That's our torque on that shaft. And the further out the force is applied, the greater your torque. So that really, on our large wind turbines, it's out the outer part of our blades that are really harnessing the most wind energy. They're really applying the greatest amount of torque onto our shaft. One of the many reasons why the blades keep getting bigger and bigger and bigger. We used to not see too many in the past few years of the onshore wind turbines being over 100 meters in diameter. But now here in Kansas, the largest ones that are now operational are 132 meters in diameter. That's about a football field and a half for the diameter of those wind turbine rotors.
So are you gaining efficiency by doing that, or there's less loss of the transfer of energy? Why so long?
You are gaining greater access to wind energy. The bigger what they call wind-swept area, referring to that diameter, the larger the diameter of that circle that the blades sweep through, the more wind energy you're able to harness. So it's just given that you can't pack them in too close to each other, the bigger you make them, the more access they have to the wind energy. So bigger is better, as long as the engineers can make them strong enough. Yes. So once you have the shaft turning, we would call that the low speed shaft, because we actually want to make it go faster. The generator needs high speed. So there's going to be a gearbox that the low speed shaft or main shaft is attached to, and then through a set of gears that's going to speed it up. And then we're going to have the high speed shaft. The high speed shaft then connects to our generator. And that is where the magic happens, although it's actually scientific and it generates electricity. So I'll talk a little bit about how we're generating that alternating current. It really comes down to magnets and the fact that it's a rotating machine. It's using electromagnetic induction. And what happens there is that you have a conductor, in this case, copper wires. They can conduct electricity, the flow of electrons. There's a force that is applied to them as they move through a magnetic field. Magnetic field is not something that we can see, but magnets have that force. It's attraction and repelling. When you take two magnets and you put north and north, they repel. When you put south and north, they attract. It's that same force there. It's an invisible force from magnets. And when a conductor moves through that, there's an electrical pressure, and we call that voltage. Voltage is electrical pressure. So we're trying to create that electrical pressure by having the shaft rotate copper coils through a magnetic field. And this is breaking it down and just making a much more simplified version of what's going on. North and south of a magnet, they have, you could refer it to as positive and negative as well, opposite polarities, and then a 360-degree rotation. So as you rotate those copper coils, the current is going to flow in one direction as you pass by the north polarity of the magnet. And then it's going to go the opposite direction. It's going to alternate, hence alternating current. It passes by the south pole. It's going to go the opposite direction. It's rotating 360 degrees, so it's going to keep going north, south, positive polarity, negative polarity. And here in the United States, 60 hertz, so 60 times a second, we are getting that polarity change. So that's the alternating current that a wind turbine will generate. And then we send it through the power line, down the tower, down to a transformer, increase that voltage, collect it all up from all the wind turbines, put it on the electric grid, and sell it to the customers.
Okay, that's the big question mark to me. You made that sound so simple, like that you increase the voltage somewhere in the middle of all that. Is that the work of a transformer? I don't know what a transformer does.
That's exactly right, Kristen.
And if you take the energy, however you define it, of the wind, and then at the end, when I plug in my toaster, what's lost between?
A lot of inefficiencies. Basically, every step of the way, there's inefficiency, there's power loss. First off, you cannot get 100% of the wind energy. To the science that we understand, it really is not possible to get more than 59%. And I'm sure there's a lot of calculations that go into that. It's called Betts' limit. So I imagine Betts is the fellow who did the research on this. 59% is the amount of wind energy that you can harness. A lot of wind turbines don't even come close to that. I mean, you're doing great if you're in the 40 percentile range. Now, once you put it through a shaft and a gearbox, there's a lot of vibration. The vibration itself is an inefficiency. If you hear the noise, that's an inefficiency. And then the generator. You're moving conductors through the magnetic field. The magnetic field has these invisible lines of flux. You're not going to pass through 100% of them. So there's going to be some inefficiency there as well. There are some electrical losses, eddy currents, copper loss, iron loss, hysteresis, all these many different energy losses. Most of them come down to the electrical energy ends up transforming into thermal energy in small amounts. Power company tries their very best to keep that as small as possible. And then also with the high voltage transmission, the whole reason why we're increasing the voltage to, let's say, coming from the wind farm near us, it goes to 345,000 volts to send it off to other parts of the state. That is all to actually decrease the current. So the electrical power, we have energy inefficiencies with the electrical power. If you can increase the voltage with a transformer, you actually end up decreasing the current. You actually decrease the amount of electrons flowing, but you have the same amount of power because you have increased the electrical pressure. The electrical power is a function of the electrical pressure multiplied by the flow of electrons, the current. So the power company is doing a whole lot with their substations, their transformers, to try to cut down on the inefficiencies because they want to sell you as much of the electricity as they can from the amount that they're generating. I have a question from Jeffrey. How does turbine control frequency as wind speed changes and blades rotate at different speed? Yeah, I'm going to let Andrew answer this one. He knows a lot more about matching that 60 hertz, that frequency.
Yeah, so since I am the DC man, I will go ahead and gloat a little bit that the turbines actually convert the AC coming from the generator, convert it to DC, because then they can invert it back to AC to perfectly match the grid. So they're using raw AC power coming out of the generator. They convert it to DC, which is just a diode stopping the flow in both directions, turns one side into AC, one side into positive, one side into negative, and then they invert it back to AC. And that's actually why turbines have gotten more efficient, not only aerodynamics, but also controlling switching losses and all that it's much more efficient now that we can closely match the grid. And we don't care what the generator RPM is now, because if it's 30 hertz or 20 hertz or 15 hertz, it doesn't matter. We can generate power and convert it into the proper AC power through the DC link, is what they call it, inside the generator, inside the turbine converter system. So good question.
To what extent does wind energy and its rapid popularity, what's the motivator? Is it cost effective, or is it more climate centered as renewable?
Well, I would say it's both. I mean, we're all getting more concerned about what are the repercussions of how we generate energy. So that's one motivator. Well, we have so many big power companies building more and more wind farms, more and more solar farms. Both of them have become very competitive. And simply put, wind energy is the second cheapest source of electrical power in the United States. Take away the subsidies, second cheapest. Currently, the number one is burning natural gas. People don't realize we've gotten to that point where natural gas is so inexpensive. They're burning natural gas just to produce electricity. So that's the cheapest right now. Wind is the second cheapest. They're making a really big profit at those wind farms. So yeah, it's going to stick around for quite a while simply because of the profit.
Yeah, Kit's right. It's the second cheapest. Only like on a national scale. In Kansas, I would say wind energy is cheaper than natural gas, only because we have so much of it. But we're not like, I guess we could easily be an exporter of energy, and at that point, be making profit to sell it to other states and that kind of thing. But
well, how far can you move this?
We have big companies.
How far can it move? what you're
What's that?
generating in Kansas. How far can that energy go and still be cost effective? Move it.
That's where we get into transmission losses and that kind of thing.
Right.
We're waiting for some big DC lines to be built. The grain belt power line, clean power line is a big DC power line that's going to go from here to Chicago, and then we're going to have a really cheap way to transport power all the way to Chicago from Western Kansas, where we have a big bottleneck right now. What they really should have done 10, 20, 30 years ago is connected all of the national grids, east, west, and central together. But at that time, it wasn't cost effective, and everybody thought, coal and natural gas were going to be, going to last forever because they were so cheap. And yeah, like nobody is building coal plants now, not because of the environmental factor alone. I mean, that's, it's a dirty power, but also that it's too expensive to, and you don't know where the price of coal is going to go. It's getting more and more difficult to find and remove those resources and ship them all around the country, and everything fluctuates so much. It's easy to transport wind energy. You just hook it up to the power line. It's easy to fuel it because it doesn't take any fuel. It just blows. It's not going to stop. That's another science of it is, the wind energy is what basically creates all of our weather and everything. I mean, it's, the wind is not going to stop. It's not something that's going to go away. We have lots of data on that. So yeah, there's a ton of factors in all of it, and a lot of it has to do with just the economics of it. It's they've actually got to the point where solar plus batteries are cheaper than wind in some places because of how affordable or how ineffective wind is in some places, and how good the sun is, like down in Arizona and Southern California. It's actually cheaper.
I want to make sure we get some solar energy in here.
Yeah.
And also to put that Tesla and Edison AC versus DC dynamic here. So go ahead and pull up your slide. I think you had one for us, Andrew.
Yeah. Did you? I don't know if you
do you want me to bring it up? I do have the one you sent me, or do you want to just pull it up on yours?
I can pull it up.
Okay.
Excuse me, at some point in this presentation, will you talk about whether transmission technology will outpace, I guess, battery technology? Right now, I understand that renewables have a big problem with storing of energy because the battery technology is not that great, but maybe it won't be an issue if transmission gets to be a lot better.
Sure, I'll talk a little bit about that while Andrew pulls up his slides. So energy storage is really going to, you could almost say, revolutionize energy transmission across the United States. There is a tremendous amount of wind energy and solar energy that just doesn't get used because the wind farms blow really strong at night. They actually produce more electricity at night, and yet people don't use as much electricity at night. So we could store that wind energy at night. And then during the daytime, if our solar power exceeds our usage, we don't currently have a standard system of storing that energy. If we can, that's a tremendous amount of solar energy that we can store up to use during peak hours. So energy storage, whatever form it takes, whether it be batteries or storing gas pressure underground or pumping water back up into reservoirs for a hydroelectric dam. There's a lot of research in many different ways of storing energy, and it's a matter of getting better returns on investment. because it all comes down to being how much of a profit is it for these companies. If we can lower, or rather, if we can improve the returns of investment, improve the efficiencies, the time of storage, the amount of energy they can hold in whichever form of energy storage, that's really going to change the way energy is used throughout our country, how it's generated, transmitted, and consumed. As far as the limitation on transmission, even if we got a great improvement in technology for what we call smart grids that can better respond to the fluctuation in solar energy and wind energy, those fluctuate. So we need smart grids to better transmit them. And we need more power lines if we want to export from a good wind area or a good solar area, export it to an area where there's high energy consumption and not much energy generation. Yes, we need more transmission. We need more modernized transmission, but that's not going to it's not going to remove the benefit of better storage technology. There will still be the issue of a lot of solar not being used, a lot of wind not being used. When we can store that and have great returns on investment for that storage, it's really going to change a lot about electrical energy transmission, generation, usage across the United States and across the world, of course, too.
Yeah, so actually, there are two parts to storage. It's actually already here. Australia has had the world's largest battery last year, or I think it was built in 2017, so about 3 years old, and it actually paid for itself in 6 months. It all depends on the use case of it. They actually had a major grid failure because of fires, and that battery saved the whole, I think, the southern half of the country or the northern half. One of the halves was backed up by that wind energy or that battery energy for 6 hours or something like that. I mean, it's a massive, acres worth of batteries. And I mean, that one event paid for itself. California now has the record of the world's largest battery, or it's under construction. I don't know if it's finished yet. I love those people. But, excuse me. But yeah, so it's going to be provided by, so Tesla's going to build half of it. I think Siemens or somebody is going to build the rest of it. So yeah, I mean, there's huge, we've made huge steps forward, and I think the batteries are here. They need to come down a little bit more in price, but they do last a very long time. And then there's actually second case uses for using the battery once they no longer are meeting the needs of that location, whether it be a car or whether it be a large solar farm. You can sell it off as a usable product to the secondhand market, which I've actually done a couple times now, and put it to use for even longer, because I don't care if it takes up twice as much space as it used to 5 years ago. I just want the energy out of it, and that doesn't matter. As long as it lasts another 5 to 10 years, it'll return on investment anyway, because it'll be that much cheaper than it was brand new. So yeah, there's actually a whole industry right now on reselling batteries, lithium batteries, from large quantities down to the secondhand market for people to go off grid or to supplement their usage. I'm actually one of them. So anyway, I'll get into this, get a couple slides in before we get any more questions. So the benefits of solar energy, so Edison was the father of DC, I would say. But obviously he didn't invent it. He just discovered it. DC there's a lot of naturally occurring DC chemical reactions and that kind of thing that are that we basically replicated in batteries. We made batteries into it, and they had this whole war. But for the point of this is the solar The sun would be the largest thermal nuclear reactor. Actually, I think it's actually the largest one in our solar system. So the power from the sun from one day is 27 years worth of energy on Earth today. Obviously, that's not accounting for increased usage in the future. And then all fossil fuels on Earth, in and on the Earth, is less than 20 days of sunlight energy. So a ton of energy, and we just need to figure out how the technology to harness it. And that's where we get into the AC versus DC. Alternating currents, obviously, you talked about changing from positive to negative polarity. DC current is just positive and negative. So you have your batteries and your car, your electrical system, all that is DC. Flashlights. The toaster would be, actually it's a universal object. It could take AC or DC. It's just a resistor. But the way an actual solar panel works is it takes sunlight and it hits the top surface here. And there's two types or two layers of solar panels sandwiched together. There's the N type and the P type. Basically, it's just the one of them has basically an extra electron, and the other one has the hole basically for the electron to fill. And so all these ions are trying to get across. And so when you excite it, the ions are trying to get across, but they can't because they're blocked. So they have to flow around because they're always going to try and find the path of least resistance. So when you hook a wire in between there, it'll flow around. And so it's actually, there's no moving parts. It's just one layer that's positively charged and one layer that's negatively charged. And you're just connecting the circuit and using a little bit of it as you do that with this little light bulb. And so that was that. The solar panels have been around since I think it was the 30s. I had to go back in my history of solar energy, but a long time, and were first really popularized in the space program. People needed some kind of energy source in space. The Russians thought nuclear energy was great. We thought, hey, let's use solar panels. We've got the technology. They're using gold-plated stuff and really making high efficiency panels. They cost a fortune, which anything in the space program costs a fortune. So that's just kind of useful or normal as usual business or business as usual. So when we started getting more efficient, I think I have a slide in here that. But here's the latest and greatest on solar energy. They have solar panels now that have glass on both sides. It's called a bifacial solar panel. And so you have glass on one side, you have a solar cell on one side, and you actually have a differently coated surface on the bottom side of that cell, and then another piece of glass. And you're actually sandwiching it between there. And so the front side is made for direct sunlight, and then the back side is actually made to generate electricity by reflected sunlight, which is a slightly different wave, UV wave, than the direct sunlight. And so on average, they can produce 30% more than a standard single-sided. And it makes sense for some cases, probably not rooftop mounted since there's no reflected light on the backside, but large solar farms where the backside is open and it's tilted towards the sun, a bifacial panel would produce a lot more energy in the same amount of area. Basically, you're taking advantage of the sunlight that's hitting the ground behind the panels, because you don't obviously want to fill up the entire space next to the panels. If you did that, you would have panels being blocked when the sun changes angles. So yeah, this is the latest technology, and it's very, very high efficiency. I don't know that there's actually like any type of a limit for it, but anyway, so what we do with solar is we actually do what's called net metering, and it's not just to solar. It's also to wind. If you had a wind turbine in your backyard, it would be the same way. But most people don't have that kind of space. So we usually see net metering as a solar energy technology. But basically you push power in from the inverter through this DC to AC inverter, or from the solar panel to the inverter. We have to produce AC in order to match with the grid so our house can run on it, or else we'd have to convert everything in our house to DC, which would not be very convenient. Shopping at the DC store is a lot more expensive and not as easy to buy secondhand. It also, they do make them DC freezers, refrigerators. I don't know that I've ever seen an oven, but they're probably out there. So anyway, so this makes the easiest way to standardize it, and there are standard inverters, but basically you just plug it into your electrical panel, and it can power your loads. And when you don't need that much power, it will send it out through the meter, and the meter will take advantage or keep track of all the energy you've turned backwards, and then you can take it back as a bank, storage bank, a credit, whenever you need it. And that's been really popular. It has been really popular for the last 5 to 10 years, 20 years. But it's becoming less and less of a thing because the more and more people do it, the less and less that power during the sunny times is valued at. It's just like anything. If you produce, too much of something, now it loses its value. And so in California, they actually have problems where they're actually, it's called the duck curve, where the curve goes to negative during the middle of like noon, and then goes back up after the sun starts going down. And so anyway, so when so now that we have this duck curve where energy is now being worth less, batteries come into play, and we want to have it. We want to be able to push that energy, save it ourselves during the middle of the day, and then push it out or use it when we actually don't have as much solar energy. And so there's a couple of different technologies. I'll go through those really quick. So string inverter, basically central inverter, and the solar panels are connected in series. So every one of those is adding up to the total system voltage. And then you have microinverters that each one of them produces AC. And so the advantage of that is it makes it simpler. Now you don't have high voltage DC running down your rooftop. You just have DC connected right to the inverter, and then you have AC running back to your box. And so you could do that in many different ways. And so they actually have a hybrid where they have optimizers which take that DC and standardize it on the roof, and then take it down to your inverter, the central inverter. And so that kind of the best of both worlds. But that's a couple different types of technologies. So the reason why solar has been getting so popular, back in 1954, one of the first commercial solar panels was 65 inches by 39 inches. It was only 6% efficient, and it only produced 20 watts, which is a third of a 60-watt light bulb. Nobody really thinks about bulbs as 60 watt. Well, I guess they think about it, but now it's LEDs, so they're not actually 60 watts anyway. But so that's kind of where they were at. And in 2012, they were 15% efficient, producing 200 watts, so 10 times more powerful. But from 2012 to 2018, they went from 200 to 320. And so basically the same exact size, they're just getting more efficient. And that's technology. Actually, today, I didn't have an updated slide, but I was going to add in that today they're over 420 watts. They have some that are like 430, 440 watts for the same size of module. And so it's been rapidly increasing. And I think we're getting to the point where it's going to stop and they're just going to make a bigger solar panel. And there are different size of solar panels, but they're getting into like the 22 to 23% efficient. But I think they've hit kind of the peak of current technology. Really, this is exactly the same technology from 1954. It's a silicon cell using multicrystalline, basically sandwiched out of a single piece of silicon and cut. It really hasn't changed that much, but they've just gotten higher quality silicon, maybe, and maybe a little different mixture, gotten a little bit better. But also, like other parts, they have a cell. You still have to wire those cells with bus bars and everything. And so they've really gotten to the point where, now they're really efficient. But also on this side of the chart, we have how much we've produced. You can kind of see 2012, it started to, 2011, it started to spike. Well, that's because price dropped significantly from $2 a watt in 2010 to less than $1 a watt in 2012. I purchased the panels for my house, at my first house, back in 2015, and I paid around 50 cents a watt. And so we're at the 60 gigawatt, and now we're up to 140 global gigawatts, and the cells are down to like 25 cents a watt. So from 2010 to 2020, it dropped, I don't know what that is in percentage, but it's a really low, really low amount, almost 100% drop in price. And that's what's caused the main reason why people are using a lot more solar now, is because it's actually cheaper to produce. It's called grid parity, where solar energy is cheaper to produce than buying it from the electric company. And so 2017, when we started the solar program, we built our own solar farm. We spent $300,000 on it, and it's a 200 kilowatt project. So we only paid about $1 a watt for the entire project. So $208,000, and it was like $1.25 a watt. And so the price has gone way down. And this chart here is the actual production we had from last year. You can see, obviously, the cloudier months don't produce near as much. But this is I think in the summer is not quite half of our colleges, the main campus, but it's a large amount of the college's energy. But the wind turbines don't produce hardly anything in the summer. And so that's kind of where we have the best of both worlds. We have solar and wind to help us produce most of our power. Other uses you guys may have seen, lighting is great. You can charge it during the day when it's not being used, and obviously you have to have a battery to make it last through the night. You guys may have seen fence chargers. It makes a lot of sense. Put a car battery out there in the field with a solar fence charger, able to charge it up during the day, and keeps them in at night when you're not around. A lot more farmers are doing this now. You put up a couple of solar panels on a well, and it runs during the day to fill the tank. And then at night, the cows, throughout the day and the night, they can, drink whenever they want. And it doesn't need to have a battery because it's just running when it's sunny out. And so as long as you can keep that, as long as the tank gets full, you have to do a lot of math as far as how much it's pumping compared to how much they're drinking and everything. But it's pretty standard math to figure it out. And it works really well. I have a lot of farmers who talk about how they love their wells. They don't have to haul water around in the middle of winter anymore. Many other uses. This is kind of becoming a bigger thing, using solar energy to charge your cars while you're at work. I mean, why not? And it also keeps your car cooler, so you don't have to use as much energy at the end of the day. Electric cars are obviously going to be the future. I see a time in my future, at least, where there won't be any gas cars. Like some of the movies you watch where they talk about gas energy. Ooh, doesn't gas explode? I think it was from one of those robot movies. Like, doesn't gas explode? Gas explodes. Like it's some kind of weird thing that people used gas to drive down the road. But I've been driving electrics for 5 years now, and it takes a little bit of a different lifestyle. You have to plan a little bit more, but definitely possible. And I can just see, 5 to 10 years down the road that it becomes the norm. We start producing pickups and stuff that have electric batteries. You'll need more electricity to be able to charge it. Solar, wind will come into more play, and less so the fossil fuel technologies. You go around camper RV parks, and you see more and more people driving around with solar panels, just because it's so much easier than trying to plug in, find a spot, or run a generator. It's silent, it's kind of natural lifestyle, trying to live in nature and not abuse it. So solar panels are a good match there. So any questions that brought up?
I have a question for you, Andrew.
Sure.
A question I was asked today, and I get this question quite a lot whenever I bring visitors to our solar farm.
Uh-huh.
I'm sure you're familiar with this question. Is there an issue with hail?
There's actually a standardized test of a 1-inch hailstone at 60 miles an hour that it has to pass. I personally have seen, actually, for instance, if there's a recent hailstorm in Jewell, in Jewell County, in Mankato, and we had solar panels that were on the roof. It damaged actually totaled out all the roofs, all the roof surface that wasn't covered by solar panels, and we took the solar panels off and replaced the roof, and then put the solar panels back on. So the solar panels are more heavy duty than the steel roofing, the shingle roofing. It's actually a sturdier roof surface than any of the other. And so literally the insurance company just had to pay to take that material off. Now in the future, when there's actually a roofing material that's made out of solar, if that really becomes a popular thing, I know Tesla's one of the is trying to do that, where you don't have to replace a roof surface underneath it. It is the roof surface. That would be even cheaper for the insurance company, because then you don't have to replace anything. You just make sure they're good, and if there's a couple that are bad, just take the old ones off, put a new one on, and you're good to go. That's what I could say is I've never seen any broken by hail in the few years the 5 years I've been doing it. But it does happen. I think more of a tornado or something that broke the foundation, knocked the building over, that kind of thing. But hail is not really, most of the time it's a glancing blow. It's not a direct hit, because the roof does have an angle. That's where really the solar, can handle a lot of torture.
How much more power can you get from having these panels track the sun? Is it like a 10% more, 30% more?
So there's two different types of tracking. There's a single axis tracking, which just tracks from east to west. That's what we have on our solar farm. And so basically it's got a steady pitch from north to south. So it doesn't track the seasonal angle, but it tracks the daily angle from east to west. And we've heard up to 20% increase. I think if we were to compare it to another equal size project, we would probably be getting between 20 and 30%, just because, for one, usually it's you find things where the sun may have been under clouds at some part of the day, like maybe right in the middle of the day, and so you lose, the ideal energy from that day. And then, but with our tracking system, we got it in the morning and the afternoon where it wasn't cloudy. So there's a lot of situations where the tracking is increasing even more than we anticipated. But it's at least 20% for a single axis tracker, and then it's roughly probably 30% with a dual axis tracker that tracks the north and south and the east and west.
Andrew, there's a question in the chat regarding solar farms in Kansas.
Yeah, solar farms in Kansas. So I mentioned that we're a little ahead of the curve. Next year there will be Kansas's largest and probably one of the tri-state area's largest solar farm. NextEra is actually the company that's going to be building it in Johnson County, and it's going to be a 500 megawatt, which takes up 35,000 acres of land. That's going to be the largest in Kansas and the largest in the area. And it's because, they've actually, I was actually told by NextEra engineer or manager that they're running out of places to put wind turbines. One, because of just ideal land and power lines not being accessible. And then two, they've had some problems with, I guess the not in my backyard issues with people that don't mind them being built, but just don't want them built on their land or in their area. And so I think solar farms are the next thing that's going to kind of hit, because I mean, a solar farm you're not going to be able to see from somebody 10 miles away. You're not going to be able to see them. So they're kind of more hidden, a little more easy to put in. There's a lot less mechanical systems. Kit's slides were about 20 minutes long, and mine were about 2 slides long. There's literally like 2 or 3 parts, and I mean, there's a lot of components, but there's only 2 or 3 different types of parts in a system. If there's a non-tracking, and there's maybe 5 more if there's a tracking system. So really simple, low maintenance. And that, I guess that's good for the owners, not so good for the technicians trying to get jobs. But if we install more and more and more of them, there's going to be troubleshooting. There's vermin and all kinds of issues. Animals and all that. So there will be jobs. It just will be not like we're used to with wind turbines. There won't be 20 technicians sited at a site. It'll be 100 technicians for the whole state or whatever, and they just travel around, troubleshooting.
Yeah. I find that all very interesting because I live actually in Marshall County.
Okay.
And we're looking at getting some wind farms in our area. NextEra is actually working on it, and there's been so much negativity, and it's just so surprising to me. And a lot of what I think is misinformation,
Yeah.
So.
See, they fought it back in 2008. I mean, Bruce Graham was the kind of the father of our program, and he ran into the exact same problems he was having back then of all the misinformation. It's just been basically in a big cycle. It went away for 5 to 10 years, and then it's just come right back full circle, and we're back to the same problems that they talked about before that aren't really problems. They're just I think one of the biggest problems is if you're not a landowner and you live close to them, you're going to find something that's wrong.
That's exactly right. Yeah.
It's just no different than the when doctors have the what is it called, the fake pill, the sugar pill or whatever, instead of the actual medicine. It's kind of made up in your head, but you don't, it may be a real condition, but it's just not something that the turbine caused. It's jealousy or something like envy rather than actual, a medical condition. And it's just kind of part of our society. We fight change, and I think it's kind of fighting the inevitable at this point.
Well, I definitely want to thank Kit and Andrew in everyone who's participating tonight. Are there any sort of last questions before we wrap up? I had kind of promised the guys it might be an hour, so I don't want to take up too much of their evening. But are there other questions? Okay.
Well, I want to apologize that Andrew and I weren't fighting like cats and dogs at each other's throats, like in the movie. Kind of a demonstration that we've figured it out. We know how we can apply alternating current. We know how we can apply direct current. They work well with the technology we have. It's very much, both of them very much a part of our daily lives and a part of our economy. We're so very dependent on electrical power now, and it's AC and it's DC together that drives our nation here.
Drives the world, yeah.
Well, thank you both so much. I think this has been a really great discussion. It was a great kickoff to Science on Screen. You have done wonderful. I hope everybody will consider joining us next Monday when we talk about sociopathic behavior, and then the following Monday when we talk about spider silk. So everybody have a great evening, and thank you so much for joining us.
Thank you, Misty.
Thank you.
Everybody for joining.
Thank you.